showed an animation the other day. I'll show the animation one more time. Why is it not possible to make the bob spin perfectly horizontally? So, this is the thing we saw, right? So if you this is conical pendulum, by the way, and it's undergoing circular motion here. And if I keep increasing, decreasing radius, this is how the oscillation looks like. Now, this is top view. So from the top, it is actually a circular motion, and from the side, it looks something like that. Okay, so this is what we saw, and there was another version of this, which is let me show you. Yeah, so that's your circular motion, and this is like from an angle, if it helps you understand. Now, if I change my mass, right, AJ, if I change the mass here, do you see I made it bigger? It's still rotating at what rate? Same rate. Let me show you numbers here. Numbers, sorry, there. Right, so let's say I keep changing my mass here, and as I make it smaller, or I make it bigger, there's no effect of it, right? But when it comes to angle, this is actually the most realistic version you can have. Okay, so I'm view query from this place. I want you to answer this question. You see, it's not perfectly horizontal. There's a small angle there. Now you may say that I didn't give the angle. I'm making an angle possible 87.7. So if I go a little further there, right. So that's actually breaking the system. This is actually possible. So this is the furthest you can go. What is the angle there? 89.9, right? I mean, if I go further than that, I know it's showing it's undergoing some oscillation, but this is broken. It's not really happening. So my question for you, and this is a question in the exam as well, why is it impossible to make the bob spin completely horizontally? So why is it not possible that you can have a motion where the object makes a perfect horizontal, like flat? Can it be possible? Now, in terms of forces, can you explain why? Yeah. Right. So bring it down, right? Okay. So why is it not possible to be horizontal? The weight is there, but then why, if there is any angle, it stays there? What's the reason behind that? So let's say if there's any angle, 0.1 degree, right? It can still maintain that motion. So why is it that any angle will allow you to remain in that motion? As in, like, you just said that there's a mass here, and the mass experiences a downward force here, right? What is that? Weight. And because of the weight, can it stay horizontal? No, right? It'll always keep moving down. But if it moves slightly down, right, it can stay there. It can stay and do its circular motion, right? So why is it that a small slight movement can make it reach equilibrium? Because weight is still acting, right? And shouldn't that mean that eventually it should just go down like that? So why is it that if there's any small angle available, right, it can then just stay there and it can do the circular motion properly? Anyone? No? Acha, let me explain. So essentially what's happening here is you need to break it down into its components, okay? So this is the rope, this is the mass here, and this is the weight in this case. There's tension here. What is the force that acts towards the center? T sine theta. By the way, theta is the angle with the vertical all the time. And what is the component that's acting upwards like that? T cos theta, right? For this thing to be in equilibrium vertically, can you tell me what's the relationship needed? Yeah, T cos theta equals to W. Isn't that what keeps it in equilibrium vertically? Now, if your angle is 90 degree, I hope you know that cos 90 is actually 0, not 1. Sine 90 is 1. So if I move at an angle that's 90 degree, which essentially means that this will become what? Horizontal. What does my component of tension become? 0. And then what is the only force acting on it? So it'll go down. However, if I do T cos 89.99, will it be able to maintain like an equilibrium? Yes, it's possible. Why? Because this is not what the 0. Now, it'll be difficult, obviously, but it is possible. And you'll find that it is actually possible. And that's our second follow-up question. And if you want to keep it horizontally spinning, right? So let's say I want to spin it horizontally, like goes like a lasso. Can I do it slowly or do I need to go fast? Yes. So the requirement is that you have to go really fast and then it can become horizontal or get very close to being horizontal. That's the next question, AJ. If the speed of rotation is increased, what happens to the position of the ball? So I'll try to do everything same, right? Tension should be maintained, and it's going in a circle like that. And if I increase the speed, naturally, you'll start to notice which way is it going up. If you ever spin something, right? If you spin it very slowly, I'll get a ball and a pendulum to show you. But if you spin it very slowly, it stays there, right? If I increase the speed, right, it will start to go up. It will go up. You can't do anything about it. It will have to go up, right? So my question is, why does it have to go up? Yes. Acha, okay. Yes, you can use that as well. P increases, right? Because they're directly proportional, everything is constant, right? Both the answers are fine, but I just have a question for you. Imagine the tension is constant and you can't change the tension. Okay, it is possible that if it's a rod, the tension can vary, and then the rod has a fixed tension, right? In that case, if you start to spin, it will still go up. Why is that so? The answer is much easier than the way you do. So why does it raise itself if you start to spin faster? So if you're spinning faster, you'll start to notice it's going up like that. Why is it so? You said tension increases, right? Which is true. But let's say tension doesn't increase, it'll still move up. So why is that so? Okay, is there anyone who wants to try it? Why does it move up? So I'll explain. Who provides centripetal force in this equation? Like in this scenario? T sine theta, right? So T sine theta provides my centripetal force. And and that would be equal to what? mv square by r, right? Or m what? Omega square r, right? So there are different equations out there. Now, if I spin it faster, what will happen to omega? Increases. As omega increases, what does sine need to do in order to maintain circular motion? It needs to increase because sine has a what relationship with angle? Direct relationship, right? So as the value of sine increases, what happens to this whole thing here? It increases as well. To facilitate the circular motion at high speeds, you need more centripetal force. To provide more centripetal force, right, at the same tension, you need what? More angle. And that's the reason why it starts to rise up. Okay. Now, what if tension can change? In that case, angle shouldn't change, right? Because if tension is changing, why would you need to change angle? Right? So that's the thing. So if tension changes in any scenario, you might notice it changes height. But if tension is constant, it'll start to rise because now the angle has to play a role. Okay. Right. So I will go through this all three one more time because it's very important for us. So I'll go with number one. Number one, there's like a this I'll provide you in a bit. The first one is explain why the speed does not change if we change the mass, right? So the answer to this is, we saw the other day, the formula for centripetal force is Fc equals to mg tan theta. This is the formula we saw. And what is Fc centripetal force? Can you tell me two equations for centripetal force? M v squared by r and m omega squared r. So yeah, m v squared by r যদি use করি আমরা, for example, should be equal to mg tan theta. And what cancels out in this equation? M. So because the mass cancels out, eventually you find that the equation is just v squared equals to v divided by r, sorry, is equal to g tan theta. Does mass have any role to play in this equation? No, right? So if you change your mass, right, it wouldn't hamper your circular motion. And there's this question, you guys don't get these kind of questions, but edX and they're very interesting. So have you seen those rides in fairs where you have like a plane and this thing spins around, right? It's not a merry-go-round, I don't know, carousel, but okay, so it just keeps going in a circle. So the chair where people sit, right? Typically, there's no weight limit. Typically speaking, okay, there's a height limit. That, you can't be less than some size, right? But mass economy effect, why is that so? Why is it that mass has no issue here? Because of this. Why? Because mass doesn't really hamper the circular motion. Otherwise, what would happen if mass was a problem? Some people might not enjoy this as much as somebody else. Why? If mass is an issue, what if this thing doesn't rise up? And then, or it rises up too much? Wouldn't that be a problem? So because mass is not a factor affecting the oscillation, any person can actually ride it and they will experience the same thing. So as it goes up and down, it'll be up and down for anyone with any mass. Why? Because mass doesn't have a role to play. Sure. Right, so that's the first thing. I'll give a small note on this. Why is it impossible to make the bob spin completely horizontally? Etar answer W equals to T cos theta. And if it's perfectly horizontal, what's theta? If it's perfectly horizontal, right, what is theta? What is the angle here? 90, right? And if theta is 90 degree, তাহলে তো আমার হচ্ছে T cos theta should be equal to what then? 0. Hence, there's no vertical component available to equate with what? Weight. As a result, it'll start to move down. Okay? So that's the other version. This is the summary of it. Okay? Our lastly, we know that centripetal force is equal to T sine theta. So if you want to go fast, you'll require more centripetal force. And for more centripetal force, you need more angle. And sine theta is directly proportional to the angle. So as the angle increases, your centripetal force increases. Okay, so FC is directly proportional to theta there. Right, so these are the different types of questions possible from here. Okay, I'll give a note on this just to copy right now. And if you have any questions, do let me know. It's all theory based here, so if you have any issues, let me know. Right, so I'll just read through this. Mass has no impact on rotation since F equals to mg tan theta and m equals to mg tan theta, so the masses cancel out, right? So we'll just cancel the mass out. So this mass cancels out. Next, the bob is made to rotate completely horizontally. Vertical component is T cos theta, which is 0. Hence, the weight exerts a resultant downward force, thus it can never maintain a horizontal position. So it's not physically possible for something to be perfectly horizontal. Why? Because if it's perfectly horizontal, what's the vertical tension component of tension? 0. But what is still acting on it? Weight, right? So it'll have to go down. Even fan blades, right? They may appear perfectly horizontal, but if you see, they're not. They're definitely not. Okay. Any other scenario that you have been told is perfectly horizontal, right? It probably isn't. Helicopter blades, for example, right? If you see in slow motion, they're actually tilted. They have to be tilted for aerodynamic reason, but it can't be perfectly horizontal. Okay. As speed is increased according to the equation, centripetal force increases. Hence, since centripetal force is T sine theta, the angle has to be increased in order to provide greater centripetal force. Yeah, you can use that as well, but some students struggle with the tan relationship. Tan is not linear. To a certain degree, it increases and decreases, right? So usually sine is easier because sine means only increase and cos means only decrease. All right, so just skim to the answer. If you have any questions, let me know. So we'll be starting a new thing today. It's a generalized topic. It's called vertical circular motion, and it's a little challenging. So it'll go here. I will upload this in Google Classroom. So just in case, if you want, just read through it, problem থাকলে বলো, and copy it later on. It'll be a revision as well. Okay. Done? Did you understand this? কোনো question থাকলে আমাকে বলো.
So what is the process? What is the motion within gravity? Sorry, without gravity, how would that spin or larger up in space?
Am I spinning it horizontally or at an angle? Yeah. Just horizontal is possible. Yeah, because since there's no gravity out there, it just needs tension. So as long as you can provide tension, it'll work. If the speed of rotation is increased, what happens to the position of the bob? Yeah. So if you remember the scenario that we had, it was a pendulum bob like that. And there are a couple of forces acting here. So there was one force acting here, which was tension. And we broke tension down, right, into two components here. The two components we had were this one and that one. Can you tell me which component is responsible for ensuring it undergoes circular motion, given that this is the center? Yeah, the angle, by the way, is always the vertical angle, unless stated. Some years they might give the other one. So if that's the angle, right, this is going to be t sine theta, and that's going to be t cos theta. So out of the two forces here, what helps me undergo circular motion or provides my centripetal force? T sine theta, right? So t sine theta, and that is equal to my centripetal force. Now let's say if you start to spin it faster, right, as the speed increases, so as something spins faster, what happens to the requirement for centripetal force? Do you need to provide more centripetal force or less, or it doesn't matter? If you spin something faster, right, do you need to provide more centripetal force? Yes. Why? If something spins faster, its velocity is higher, and the change of velocity would be higher as well. And because change in velocity is higher, what would be greater? Acceleration. And because of a higher acceleration, centripetal force must be higher. So that means this must be a large force. Now, if I assume my tension is constant, okay, it could change, but let's say it is constant. What does sine need to do in order to allow a higher centripetal force increase, right? And if you know sine increase, it means that as this theta here, sine theta increases, sine theta is directly proportional to theta. Do you know that? So sine 0 is 0, sine 90 is 1. So if I want more sine theta value, do I need a more theta value or a smaller theta value? More, right? So as a result, what will happen? It'll start to get higher and higher and higher like that, but you'll never be able to attain what angle though? 90, because the moment it becomes 90, it is good for circular motion, but that component that was overcoming weight is more there. So the system will naturally move downwards. Lift. In that case, you don't need tension. The object has an external force acting on it. It can be possible. So let's say your object has wings, right? Then the wings will experience an upward force, and that can keep it afloat. It is possible. Is it okay for everyone? Acha. So আমরা এখন হচ্ছে art জিনিস করবো. This is conical pendulum. So there are different pages with different concepts out there. You can go to page 14. It's vertical circular motion. আর যাদের বইতে মনে কি প্রবলেম ছিল, did you change the book? দেখতে পারো, বলে চেঞ্জ করে দেবে। Right. So the thing I'll be doing right now in context of your exam is very popular. Like, so far, whatever challenging questions have shown up, they came from this thing called the vertical circular motion. Okay. So before we start, I just want to clarify something in case you haven't done the previous classes. Circular motion can be of two types in terms of circles. One is this one, the one that we talked about ekdom shurute. Can anyone remind me, what did we call this? Yeah, horizontal circular motion or horizontal centripetal force here. So you have a mass and there's a rope that's making it go in a circle. This is the center, and this is perfectly horizontal, right? So if it's perfectly horizontal, which by the way, is it possible? No, right? So this is hypothetical. It's not really what happens, right? So that means there's what been provided towards the center, tension, and the tension that's provided here happens to be your what force? Centripetal force. So can anyone tell me what's the difference between centripetal force and tension? Category. Right. So in this question, right, who provides centripetal force? Tension, right? And can centripetal force be a force on its own? Can I say that the force that keeps my object in circle is centripetal force? It has to be a different force that applies that force, right? Yeah, so just to clarify, centripetal force is not the name of a force. It's a name of a type of force that helps you undergo circular motion. In this particular question, who provides the centripetal force? Tension, okay? It could be something else somewhere else. And in our scenario now, you'll see that it varies, okay? In a single scenario, it can vary. So this is referred as the horizontal circular motion. And right now we'll do the vertical one. So don't write anything, just observe how it works. So vertical circular motion is like this. And the analogy I had provided you was that ceiling fan versus what fan? Like if you want to understand, table fan, okay? So your table fan would be what motion? Vertical circular motion, and your ceiling fan would be what? Horizontal. Basically a circle that goes like this, that's a vertical, right? And a circle that goes like that, that's horizontal. So this is vertical circular motion. Let me set the premise here. So the premise of it's undergoing circular motion at a constant rate. So it's something like this, like that. So it's undergoing circular motion at a constant rate. If it's a variable rate, like slow and fast, right? Our math wouldn't work. And why did I do this constant rate thing? Because again, revision of our first class, in our A2 circular motion, right? We deal with what circular motion? Constant or uniform circular motion. Okay, if your circular motion starts to vary, it is too complicated for your A level. Okay, so some question right. So you have your mass here at the top. So it's a mass that's been spun in a circle. And we will investigate 4 different locations here. So one is at the side, like how the forces act on it. One is on that side here, and one is at the bottom. In between it, আমাদের syllabus আসার chance নাই, because the question will become too complicated. Okay, and so far যত question আসছে ওরা ওই পাঁচশোগুলো জিজ্ঞেস করেন না, only these 4 locations. And there's a rope that's keeping this in a circle. So that's the rope, and this is the center of the circle. Okay, so are you clear about this? So basically the circular motion is like that. It's been in a circle. It's obviously at 4 different spots that I've picked it out, right? Acha. So first question, can anyone tell me which way is centripetal force acting? I'll give them names. At A, at B, at C, and at D. So where is centripetal force acting at A? Towards the center, right? Shouldn't come as a surprise to you anymore. What about B? Towards the center, right? So আশা করি তোমরা বুঝতেছো that centripetal force will always have to inevitably act which way? Towards the center, right? Okay. But the problem is, who provides the centripetal force? That is a little challenging here. So before we start that, can you tell me, are you aware of any force acting on the red ball right now? Weight, right? So we'll just label it for the sake of it. So there's weight here, W. Do you think there's any force acting at B? What? Weight, right? So weight হচ্ছে কিন্তু a no-brainer. It's gonna act where? All the places. কোন দিকে? Downwards. So এখানেও তোমার weight নিচে দিকে act করতেছে। And এদিকেও তোমার weight নিচে দিকে act করতেছে। Okay, fine. That's enough for weight. Now, can you tell me, at the top, right, centripetal force is acting downwards, right? And weight is also acting downwards. What can provide my centripetal force at the top? Weight. Okay, so my weight here can provide centripetal force because the requirement was, do you have a force acting towards the center? And if there's a force acting towards the center, what can it help you do? Provide centripetal force, right? So you can weight help করতে পারবে now. We'll come back to that later on. But what about here? Can this weight help you undergo circular motion? No, right? Why is that so? Because it's acting downwards, but you needed force which way? Sideways, right? Any recommendation what might be able to provide force here? Tension. So you'll notice this rope suddenly has tension here, and T is acting this way. What about D as well? Can it sustain circular motion just using weight? No. Why? Because weight is acting downwards. I need a force acting which way? Towards the center. So there must be a force to help me go towards the center. What should that be? Tension. Let's come to C. C, can weight help undergo circular motion? No. Why? It is acting along the line, but is it acting towards the center or away from it? Away from it, right? So tension has to help here as well. And finally, at the top, who's acting towards the center? Weight. And what is needed to act towards the center? Centripetal force, right? But here's the problem. I'll explain what the problem is. Let's say my centripetal force requirement is 100 Newton. Mane, the object, in order to go in circular motion, needs a force acting towards the center of how much? 100 Newton. What if your weight is 10 Newton? Yes, it's acting towards the center, but is it enough? No, right? Do you see it's not enough? So how can I make it enough? Can I change the weight? No. So only if somebody else would come and help me. What is the tension, right? So again, tension will come here and help you out. So these are the forces acting on the object at different places, right? Tension taking the top will only become a thing if weight is not enough. Do you get my point? Our baki shop tension is mandatory. Do you get my point? Okay, now let's try to understand what is my centripetal force going to be in terms of equation at these four places. And then you'll find an interesting finding. Okay, we'll start with A. So at A, can you tell me an equation for centripetal force? Who provides centripetal force at the top? W plus T. The weight is applying, right? And then who comes and helps me? T, right? But actually, who gets priority here? Weight. So weight will try to provide it because it's naturally there. If weight can't provide, who will come and help? Tension, right? Okay, fine. So this is weight plus tension. So eventually, what is tension going to be at the top? FC minus weight. আচ্ছা আমরা টেনশন নিয়ে কাজ করব তো তাহলে টেনশন সাবজেক্ট বানাচ্ছি। So yeah, this is the equation at the top. Can you tell me what would the equation be at B? Yeah, that's it. FC equals to T, right? Our কিন্তু হচ্ছে at B, weight has no real role to play here, right? So at B, it's just FC equals to what? T. FC equals to T. So that's the equation here. See if you can answer this on your own. What is the centripetal force going to be equal to at the bottom? T minus? Why not W minus T? Yes. I need a what force acting towards the center to sustain circular motion? A resultant force, right? Not zero, resultant force. How can T be a resultant force here? If T is equal to W, less than W, or greater than W? Greater, right? So it's going to be T minus W. So eventually, T is going to be what? FC plus W. Okay, a equation will make a sense in a minute. Just that key see. And let's see the bigger picture right now. So what is the other T going to be as well? FC equals to T, because they're basically the same thing, right? Now, can you tell me, as I spin this thing, where is my tension the greatest? As I spin this thing, where is the tension the greatest? C. Why? Because C tension is FC plus W, right? Can you tell me where is tension the least? A. Because at the top it's FC minus W. And can you tell me where is tension exactly equal to what my centrifugal force is? B and D here, right? Now, why did I explain this? Because the questions that have come over the years, when you're spinning a mass, right, heavy mass, and you're spinning with a rope, where is it most likely to tear? At the bottom, okay? Because when it's at the bottom, it's been pulled the most. Tension is the greatest, right? And sometimes as you spin something, you feel that the rope doesn't become slack. Do you know what it means by slack? So you're spinning it, it's usually supposed to be taut means tight and straight. But sometimes it can become slack like that. Where is that most likely to happen? Yeah, so Ate, what if your centripetal force requirement is 100 Newton and your weight is also 100 Newton? How much is your tension? Zero. And when your tension is zero, right, what do the rope look like? Slack, right? There's no force on it. You get my point? So I don't know if you ever felt it, but let's say you tie a very heavy mass to a rope. As you spin it, right? If it's too heavy, they go over a gear, it just goes and just falls down. Have you seen that happen? Why? Because the weight is too much and it doesn't need that much force. It just goes down straight away, right? So yeah, that is your vertical circular motion. I'll add some notes here, but বুঝছো জিনিসটা এই ইকুয়েশন গুলো এক্সামে তোমাদেরকে অন স্পট হচ্ছে ফিগার আউট করতে হয় that's the problem. That's why I went through this. Okay, it's not really part of our syllabus. If you go to the syllabus, they have no mention of vertical circular motion, but questions are based on that. So that's what I'm trying to build like an idea for you. Say কি আসতে পারে. Okay, আরেকটা জিনিস করি before we I let you guys copy this. They give you a graph here, and this is the most latest question that came. The graph is based on angle or position versus the value for tension in the rope. Can you guys tell me if I start with zero being vertically upwards, right? Or I'll place position here, the easier of it. So if this is A, B, C, and D. Can you tell me how this graph look like? Sine or cosine or negative cosine or positive sine? Tell me the exact thing. Yes, very good. But is it going to be cos? If I start from A? No, the value would be low, not zero. Because, I'm saying a scenario where weight is needed. Okay, so what should the graph look like? Achha, I'll help you out, don't worry. So can you tell me at A, is tension the highest, lowest, or like optimum? Lowest, right? Okay, so it'll start from here. That is at A, so that's my tension. It's lowest. At B, what is my tension? Highest, lowest, or optimum? Beat it. Optimum, I mean, the exact amount you need, right? At C, what's my tension? Highest, right? Lowest or highest? Highest. At D, optimum. And the pura cycle darker. So there's an A here again. So at A, it's back to what? Lowest, right? If I join these points here, what kind of a graph do you expect? Is it going to be so it's shaped key sine? No, this graph. It's negative cosine. Acha, let's do graphs first of all. This is sine. This is negative sine. This is cosine. This is negative cosine. Which one did I draw? Negative cosine. Achha, so negative cosine, however, it's a little elevated because my value is not 0. Jyoti 0 hoyo thake, it will still maintain the same what? Shape. But do you know there's this thing in math called translation? So the graph will get translated to this point. That's when what happens if there is no tension needed, right? The weight is enough. But weight is enough now, it has to super clear. So yeah, that's the graph that came in the exam. They asked you to sketch the graph. This is how the graph will look like. Anyways, আমি হচ্ছে draw করে দিচ্ছি, একটু copy করে দিও the circle and the graph.
So how do we know that the relation is like non-linear?
Non-linear, because if you go from A to B, this is tension and this is angle. What was the formula for the tension? So if we can relate to our previous example, the conical pendulum, right? What was the vertical component? T cos theta, right? So it's a cos function. And we are dealing with the vertical components here everywhere. Because, you know, this is the vertical component. So as I'm spinning, the angle is changing with a cosine function, right? So that's why it's a cosine graph.
So it's always going to be a
Yeah. No, it will depend where you start your graph from. So if I started from B, it'll be a sine graph. So it gets shifted based on your point of reference. Are your schools open? Mastermind clinic? Uh, really? Yes. I don't know if the scoring is the same right now or not, but back in my time, it was like out of 800. No, it was 800. Subject essays or the overall general one? That was out of not 2400, 1600. It's still 1600. Yeah, I don't remember. Something that's not memorable, probably. Because I've heard so many SAT scores, I don't remember which is mine. It wasn't that bad, but it wasn't like full, which a lot of people get. Like, very close to full. And there's something called subject SAT. Do you have them right now? Oh yeah, so I get that math and physics. So that was very close to full. But the general one I don't remember. Are you planning to give your SATs? Is it not computer based or you have to still write on a paper? Oh, okay. So it's like GRE. And it's like adapted questions or linear questions. Like in GRE, it's like if you do something bad, it'll give you like an easy one or it's like that. You can do better in that. Oh, you're allowed calculator? Yeah, I mean. Are you guys done? We'll move on to new things. Okay, so label for the graph before I start the other part. Next part is quite interesting. So it practically notice for Toro. But can you tell me the labels on the x-axis? Sorry, y-axis. What are the labels? Dotted line that they help for it, this is T. So what should the highest point be? Yeah, this is going to be T. It's going to be FC plus W. Don't subject it to T, obviously, right? Our niche take hobe FC minus W. Anyways, let's move on. This one is called takeoff velocity. So you have two quantities like this in your syllabus. One is called escape velocity and the other is called takeoff velocity. They're very different and we have both of them. So to clarify, escape velocity is used by rockets. So when a rocket takes off, right, it needs to have a certain velocity to escape the Earth's gravity. It's called escape velocity, right? This is different. This is called takeoff velocity. And this one is used by cars or bikes to take off from the ground. So let me explain how it works.
They don't fly.
They fly momentarily, and what brings them back down? Gravity. Okay, I'll explain that. Okay, right? So imagine you have this ramp here, and this ramp is like a circle. Okay, so most ramps are actually partly what? It's like a arc of a circle, right? So this is your circle here, and this part that's at the bottom is not really there. It's an imaginary part. Okay, so I can like take this away if you want. But do you understand the upper part? That's basically the ramp. Now imagine there's a bike trying to go over this ramp. Okay, so right, so there's the person on this bike, and this bike will go over this ramp right now. And turns out, as the bike goes over this ramp, there's a particular velocity at which the bike will take off. So let me explain. So the bike will go like this, right? And most ramps actually have like a very smooth incline before it takes off, right? So you normally wouldn't find this part, but let's say you're at this part. And as you go like this, generally speaking, you'll actually stick to the road, and then you'll go down like that and just go straight down, right? However, if you go at a certain speed, right, your bike will actually take off. And it turns out it's actually based on circular motion. So we need to figure out what is the speed at which a bike needs to travel so that it takes off. It's called a takeoff velocity. So for that, the first thing you need to figure out is how is it circular motion here? Okay, so let me explain how it's circular motion. So if I take this motion here and observe just the top part, can you tell me what are the forces acting on the bike at the top? Yeah, there's weight. And this is a little different. What else is acting on the bike at the top? Thrust. Okay, thrust also. Thrust. No, thrust. Yeah, contact force, normal reaction force. Okay, so let me show this diagram one more time. Ajay, if you look at the top here, there are two forces here. One is the force that's acting downwards like that, which is what? Weight. And what is the other force acting here? Upwards. Contact force, normal reaction force, R. Do you agree? Well, I've not gone into complexities of circular motion yet. I'm just saying there's a bike on a road. What are the two forces acting on it vertically, right? So what are the two forces? There's reaction acting upwards, and what's acting downwards? Weight, right? Now, if this bike does want to undergo circular motion, it needs to have what acting towards the center? Centripetal force, right? So that's the requirement, that if you want to undergo circular motion, you must have centripetal force acting towards the center. Now, because we have done vertical circular motion, right, I feel you should be able to answer this. Can you tell me what is the equation for FC here? Is it equal to W, or is it W minus R, or is it W plus R? W minus R, right? Very good. Why is that so? Because I need a what force acting towards the center? A resultant force. And a resultant force is only possible if W is what compared to R? More, right? So it's W minus R. I'll give you a hint here. And if you remember from your AS, you might find this easier. Have you done questions on lift, like in mechanics? Physics is chilo, but mechanics are basic. Okay. Do you remember how the reading on the weighing machine would change as the lift moves around, right? Basically, that's the criteria here. So if your object has a resultant force acting downwards, then how would W and R compare? W has to be what than R? More than R, right? Okay. So since it took butcher, hopefully the next part will be easier. So question is, why does the bike take off at a certain speed? Now for that, I need to teach you something, which is when you take off from any surface, right? One of these forces here disappears. Which one? It's called free fall. So when you're free falling, right, there's what acting on you only? Weight, right? So it's called weightlessness. There are many names to that, but my point is when you're flying in the air, right, attached to nothing, there's only weight acting on you. And what's your reaction? Like if you're in the air, right, what's your reaction force? Air resistance, good. But let's say there's no air out there, or air resistance is negligible, right? What is your reaction force? Zero, right? Do you know People actually pay a lot of money just to experience that. It's called weightlessness. So whenever you do bungee jumping, right, you're paying money for zero what? Reaction. Literally, that's it. Zero reaction is judge. When you go for skydiving, the first 17 seconds, or sometimes even less, you are experiencing how much reaction? Zero. That feeling, right? It's called weightlessness. And people pay a lot of money to just experience that, right? So, whenever you jump, right, what is initially the only force acting on you? Weight, right? Is there reaction yet build up? No. As you start to fall, what starts to act on you? Like, for a bungee jump, there's the rope pulling you back. For skydiving, what pushes you back? Air resistance or the parachute, right? So, if this bike has to take off and go into the air, what should R have to become? Zero, right? When R has to be zero. So let me explain in terms of numbers, okay? Let's say my centripetal force requirement, and listen carefully, it's too complicated. My centripetal force requirement is 1000 Newton. And the weight of the car is 4000 Newton. Do you think this object can sustain circular motion? The centripetal force needed is 1000 Newton, and the weight of the car is 4000 Newton. Do you think circular motion is possible? Yes, because your requirement is met by the weight. What if my centripetal force now increases to 3999 Newton? Will it still be able to undergo circular motion? Yes, but just barely, because it's almost there. If it goes to 4000, তখন একটা interesting জিনিস হয়. When this is 4000 and this is 4000, right? If I put it in my equation, my requirement is 4000 and my weight is also 4000. What is reaction? Zero. And in physics, zero reaction means only one thing. You're not in what with the surface, contact. And that's the moment this car will lose contact with the ground and will take off, right? And for that to happen, whatever velocity is needed is referred as what velocity? Takeoff velocity. So how can we find this takeoff velocity? So Fc is equal to W minus R. And for takeoff, can you tell me what should be zero? R, right? For takeoff, R must be zero. So if R is zero, what do you have here? Fc equals to W. Do you remember what's the formula for centripetal force in terms of velocity? Mv squared by R, right? Mv squared by R. And do you know what the formula for weight is? Obviously, mg. Again, like a observation, what happens? Mass cancels out. So that's why it might come as a surprise, but your car taking off doesn't depend on the watt of your car, the weight of a car. There's no speed bumps work. Speed bumps again, the humps on the road, right? If it worked for different cars at different speeds, wouldn't it be unfair? Let's say you have a heavy car and you just go over it, your car doesn't do anything. And you have a light car, it always takes off. That'd be unfair, right? But it never happens. Speed bumps work very well because the name kind of gives it away. They work on the watt of the car. And you'll see right now why. V is equal to what? Rg root over. So the takeoff velocity entirely depends on the watt of the hump, the radius of the hump, right? So that is what takeoff velocity is. And it's in the math that so imagine you have a speed bump that is 2 meters or 50 centimeters, okay? Can somebody do the math and find out what's my takeoff velocity at 50 centimeters? Just you need two quantities here, which I've provided. 2 point? Yeah, so can wait for what takeoff velocity is, so this equation has to be derived in the exam. V equals to R. R is 0.5 into 9.81 root over কত আসে? 2.21. Right, so if your car goes over this hump at 2.21 meter per second, what will it do? It'll take off, right? Anything that goes at 2.21 will do what here? Take off, okay? So if speed bump you have to slow down so that the car doesn't take off, right? So that, the centripetal force needed is not too much, right? So that's takeoff velocity, another type of question that we have in our syllabus. Are you guys clear? Question takeoff velocity. Can you tell me how can I make my ramp or design my ramp so that I take off very easily? Do I make it like with a smaller circle or a bigger circle? Like smaller radius or a bigger radius? Bigger radius. Acha, আমি তাহলে help করি তোমাদেরকে. Have you seen in roads of Bangladesh there are some speed bumps that are like flat? They're flat, right? And there are some speed bumps that are like that. Like multiple road like speed breaker. Where are you more likely to take off? The ones that are flat like that, or the ones that are like sudden bump? Sudden bump. So that's why you'll find that if there's like a boulder or some kind of pothole in the road, your car is more likely to what? Jump, right? But if the roads are smooth and all like that, it's less likely. Why is that so? If it's like a pothole, right, the radius is very small, so your takeoff velocity is very small. But if it's a large, like smooth manabuchu, it's a very large circle. Takeoff for a difficult. You need very high velocity for that. Okay. Anyways, so our next classes will do the other examples. We are done with the chapter, so just review for you. So imagine the formula here, this one, omega equals to theta by t or v by r, right? So imagine your velocity is constant. You're rotating at a constant rate, right? The further you go away from the circle, what would your omega become? Smaller. But this is only possible at what velocity? Constant velocity. So this is one thing you can add here. So if it's a very large circle and you want to maintain the same velocity, right? You have to go slowly because aren't you covering greater distances in the same time? So, but this is again, if you want, you can add it here. It's just for constant velocity.
Sorry, my name is Shaiyan. I just joined this Thursday, so.
Oh, right.
Yeah, right. So this is my first class with you. So I was gonna ask you, how do you think I should recover the content I've lost last 5 classes?
Right. So I generally upload all the notes that I have in the Google Classroom. So you find all the classwork there.
So I should just go through those?
Yeah, if you go through those, are quite self-explained. So I feel you should have some understanding.
Yeah, yeah.